In Concept F, we're going to be continuing on with our equilibrium topic and focusing on something called Chatellier's principle. So a quick little review. When we have a system at equilibrium, the rates of the reaction will be equal and the concentrations of the reactants and products will stay constant. So rates equal, concentrations constant. However, sometimes we don't want our system to actually remain at equilibrium. We want to force that system to either produce more products or produce more of our original reactants. So Chatellier's principle deals with taking a system at equilibrium, subjecting it to a stress such as temperature, pressure, changes in concentration. The system is then going to, what we say, shift to regain the effects of the stress, or relieve them, I should say, and then they're going to attempt to regain that initial equilibrium. A shift is temporary. It's going to cause the forward or reverse reaction to take over for a period of time. Now, the shift will occur in the direction of whichever reaction was made faster by that initial stress. This will cause a change in the rates until equilibrium is achieved again. So I'm going to be using two terms, a forward shift or a shift to the right, and a reverse shift or a shift to the left. A forward shift is going to cause an increase in the concentration of products. So anytime we shift to the right or have a forward shift, that means we're speeding up the forward reaction to produce what we're moving towards, which is the products. A reverse shift means we're shifting to the left, we're speeding up the reverse reactions, and whatever we move towards, we're going to be producing more of. So a reverse shift or a shift to the left is going to produce more reactants. So keep this in mind. Now, one thing I want to point out that does not cause a shift is the use of a catalyst. Now, this decreases the activation energy of both the forward and reverse reactions. So it speeds both the forward and reverse reactions equally. So there's no shift that's going to occur when a catalyst is introduced to a system. Also, things like surface area, the addition of an inhibitor, which is basically the opposite of a catalyst, have no effects on equilibrium. So keep this in mind. It's a small detail that sometimes pops up when we look at different questions. All right, our first stress deals with our reactants. When we add reactant, we increase the number of collisions between those particles, making the forward reaction go faster. Since we're shifting to the right, we're going to increase our products because we're moving towards those, and our reactants are getting used up and decreasing. If we do the opposite and remove the reactant, we're decreasing that number of collisions between the reactant particles. We're also getting them out of the way of the reverse reaction that's going to take place and go faster. So because we're going to be shifting left or increasing the rate of our reverse reaction, we're going to produce more of those reactants and decrease our products. Now, if we look at our products, it's basically the same idea. If I add product, I'm going to increase the collisions between the product particles, making the reverse reaction go faster. So this causes whatever we're shifting towards, the reactants to increase, and what we're shifting away from, the products to decrease. If I remove products, I'm going to slow down my reverse reaction. My forward reaction will actually go faster, which causes our products to increase and our reactants to decrease. Some students like to think about whatever we take out, we're going to try and replace by the system. So we're always going to shift towards what we're taking out, and whatever we add is going to be able to get used up faster, so we're going to shift away from what we add. So this is something that sometimes helps students. We shift away from the side that was added to, so the two A's, and we shift towards the side that was taken from, so the two T's. So something to help you kind of memorize this stress of changing concentration. Temperature is another stress. When we increase temperature, we favor the endothermic reaction. So we're going to shift away from the side where heat is located to absorb excess energy. When we decrease temperature, we favor the exothermic reaction. This causes the equilibrium to shift towards the side with heat in order to release some of that energy. Now, depending on the direction of shift, we'll determine if our products or reactants increase or decrease. If we have a forward shift, our products increase, reactants decrease. If we have a reverse shift or a shift to the left, our products are used up and thus decrease, reactants are being produced at a higher rate, so those increase. So here's one way to remember it. You're going to locate in your equation where heat is located. You can see that our forward reaction is an endothermic reaction, reverse reaction will be exothermic. If I increase temperature, if that's my stress, I'm going to shift away from the side with heat. Okay, so think of increasing temperature, you're getting warm, you want to move away from heat, so you're going to shift away. So this would be considered a shift to the right in this example. If I decrease temperature, I want to shift towards the side with heat. So in my example, I want to shift towards the left, okay, in order to give off that heat and regain equilibrium. All right, another stress is pressure when we deal with gases. This causes when we increase pressure, we're going to shift towards the side with fewer moles to relieve some of the pressure that is occurring. If we decrease pressure, we're going to shift towards the side with more moles of gas. The change in concentrations is going to depend on whether it was a forward or reverse shift, just like temperature. So 3 events occur under Le Chatelier's principle. A stress occurs, temperature, pressure changes in reactants or products. A shift occurs left or right. Now, this is the crucial part for what we're going to be doing next. Concentrations of whatever is being shifted towards is going to go up. The concentrations of what is being shifted away from is going to go down. All right, so let's put this all together and look at an actual example. So say I add nitrogen gas. What occurs? Well, whatever I'm adding to, I'm going to shift away from. So I'm going to be shifting right. Now, whatever I shift towards is going to go up. Whatever I'm shifting away from is going to go down. So here again, I'm shifting right. I'm going to be decreasing my amount of hydrogen and increasing my amount of ammonia. Removing N2. So I'm taking out some of my N2 over here. I'm always going to shift towards what I'm adding to, or removing. Think about trying to replace it. Whatever I'm shifting towards is going to go up. Whatever I'm shifting away from is going to go down. So here when we remove N2, we have a shift to the left. We're increasing H2 and we're decreasing ammonia. All right, basically H2 is going to be the same as N2. Okay, I'm going to see that for H2, I'm going to cause the exact same thing, shifting right, decreasing my other reactant, increasing my product. For 4, same thing as when we removed N2. I'm going to shift to the left. I'm going to increase N2 and decrease ammonia. All right, so now let's look at adding a product. If I add my product and I add over here on my product side, I'm going to shift away from that side, meaning I'm shifting to the left. I'm going to increase what I'm shifting towards, decrease what I'm shifting away from. So I have a shift to the left, increasing my original reactants until equilibrium is regained again. If I remove my product, I'm going to shift towards the side that I'm taking from. So I'm going to be shifting to the right. I'm shifting away from nitrogen and hydrogen, so those are going to go down, and then I'm going to be trying to make more of that initial ammonia that I lost. So shifting right, and I'm decreasing what I'm shifting away from. All right, changing temp. The only thing I'm worried about with temperature is where my heat is, over on the right. So if I increase temp, think about you want to get away from that heat, so I'm going to shift away from it and go to the left. So whatever I'm shifting towards, I'm going to go up. Whatever I'm shifting away from goes down. All right, now if I decrease temp, I want to move towards the heat. So I'm going to be shifting to the right. Whatever I move away from goes down. Whatever I shift toward goes up. All right, pressure. This is where we need to count the moles of gas. So let's see if I have this on here. Ooh, I have on my left 4 moles of gas. I would fill that into your packet. And then on the right, I have 2 moles of gas. So when I increase pressure, I shift towards the side with fewer moles, which is going to be my 2 ammonia molecules. When I do that, same thing as my other 8 examples, I'm going to decrease what I'm shifting away from, increase what I'm shifting towards. So this is what I'm left with. If I decrease pressure, I want to shift towards the side with more moles. So I'm going to be shifting to the left, and same thing as before, increase what you're shifting towards, decrease what you're shifting away from. All right, we are going to be working on this a lot for the next 2 or 3 days, helping you understand this. But definitely take a minute, look through your notes, and then come to class prepared.